I wanted to remind you guys at the end of last class that you're going to see something on your final exam you maybe have never seen before. And it's something that I call a reaction roadmap. Other people might call it that too. I don't know. Sometimes I make up things and I can't always remember. Those of you that have already looked at the practice final. Sweet. So then you might have an idea of what I'm talking about with this reaction roadmap. For those of you that have not, I don't want you to show up to the final exam and be flabbergasted. That's so rude. They changed it to me while I had my back turned. Oh, also, what? Come on. I used to end the semester on Diels-Alder reactions. And this semester, for the first time, I didn't end on Diels-Alder, and I might change that going forward, which usually means the last reaction I teach is Diels-Alder, and then I can say, have you ever seen Diels-Alder anywhere before? Have you, outside of lab, obviously, have you seen a Diels-Alder reaction posted anywhere? You've been looking at it every time you come to Canvas. This is a Diels-Alder reaction that I invented because I thought it looked pretty. And someone suggested that I try making it, but I'll be damned if I try making that. Like, this is okay, but do you know how many chiral carbons are in this product? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 chiral carbons. Okay, to be fair, actually, 2 of them here are achiral, and then another 2 of them here. So there's 4 carbons in this structure that are chiral that must have that chirality in the precursor, which means that this ring has to have very specific chirality, which makes it very hard to make this polycyclic structure. So if any of you are interested, have at it, but I invented it. And it's cool, right? Have you guys ever thought about that reaction when you come to Canvas, or do you just look at it and say, molecules, moving on?
I have noticed the longer class has gone on, the more it's like, oh yeah, that doesn't look like absolute random garbage.
It doesn't look random. I do that on purpose. I put something that should look like nonsense on the first day of class so that by the end of the semester, you're like, well, there's a conjugated diene, there's 2 ketones, I make a polycyclic structure. Okay, thank you for hearing me out. When you come to the modules tab, head down to the final and look at the summer final. Remember, the key is there so you can practice with yourself. I didn't send out my reminder about tomorrow's STEM sessions, so I'll try to do that tonight maybe. 2 review sessions tomorrow. Try to take advantage of it. All right, much like your midterm, we've got multiple choice problems. Much like your midterm, you have some short answer problems as well. This time, short answer involves mechanisms. I am guaranteeing which mechanisms you can expect to find. All the mechanisms that we saw throughout the semester. So that we said we were learning over the semester. HX addition, acid catalyzed hydration. X2 addition, halohydrin, haloether addition. That was from Unit 4. And from Unit 5, SN1, SN2, E1, and E2. And what I like to do is give you an option between sets of those. So over the summer, they had halogenation or HX addition. And they had E1 or SN1. So there's 8 possible mechanisms that you could be tested on, and you'll have basically the selection at 4 of them. 2 from Unit 4, 2 from Unit 5. This is the roadmap. And it's truly a beautiful thing. The roadmap is a way to test you on predicting reactants of products, predicting products. Oh my God, that sentence didn't make any sense. Predicting the reactants of reactions, predicting the products of reactions, or predicting the reagents of reactants, and oftentimes performing a multi-step synthesis, meaning you have multiple blanks in a row and you need to solve for all of them. One of the things that I like the most about roadmaps is that there's always something you can earn points for in here. You don't need to know the whole picture to be able to find something that you can get. Here's an alkene. You probably can find the reagent that gives you this vicinal dihalide, even if you're confused about the product that should form from hydroboration oxidation. And then there's this part of the roadmap, right, where you've got this reaction over here that gives you an epoxide. Well, we know reagents and starting materials to give us epoxides. So we actually are backtracking our synthesis, and we know that we get to whatever this precursor is, an alkene precursor, by means of partial reduction, partial hydrogenation, which tells us the functional group that came before it. So if I felt confused at all about this SN2 alkylation, I don't need to feel as confused because I can actually find information backwards. I like the roadmaps, but I do know that that looks really intimidating if you've never seen it before. And you had a glimpse of this on your unit test. You had to solve for some unknown chemicals and intermediates. But this can feel really daunting if you have no idea what's going on. So practice this for sure. Okay.
Actually, question for you.
Mm-hmm.
With the going back to the three equivalences thing, does it matter if you use NaOH or NH2?
Say the first one again.
NaH.
No, it does not. I thought you said for, but now I understand you were saying or. Those are both strong bases, specifically with pKa's that are higher than the pKa of the alkyne. I think active actually showed you that you can form an alkyne by this dye elimination using sodium hydroxide or potassium hydroxide, even though hydroxide is not nearly as strong of a base. But hydroxide would not be able to deprotonate this. Oh, I'm going to sneeze. Oh, I'm walking away from my mic, but it's going to make sneezes really loud. Okay, good question. 2 answers, perfectly acceptable. Someone had brought up multi-step synthesis as well. Whose question was that? Do you guys remember? Any context towards that? Was this kind of what you were thinking about?
Yeah, just going over a couple more examples of it.
Sure. I'm actually starting to feel more hesitant or unsure that you will have the spring final when you go to the STEM Center. So I think let's do an example of that right now. Let's use the spring final as a chance to look at some roadmap problems. The other thing that can be a little challenging about roadmaps is that I try to have fun with them, and some people don't like it when I have fun. So you'll notice that this roadmap is a circle. It actually starts up here, and you take the same starting material in 2 different directions and bring the 2 different products down together to do a Diels-Alder reaction. And Aiden wanted to talk about Diels-Alder, so this would be a good one to look at. And in this multi-step synthesis, there's also a circle, because the same starting material comes around to give two different products that ultimately react together. So I know they can get a little tricky. Just read the arrows and start anywhere. There's no wrong place to start.
For that bottom left, is the arrow going from the box above that, or is it going through both steps to that box?
Right, so this reaction forms a product. Can you describe the product of this reaction? If you can't, do you have the tools to help you describe the product of this reaction? And will you have those tools on the final exam? Here's the, do you want to describe it? Who wants to describe the product?
You'll have a syn addition,
Mm-hmm.
and you'll have alcohol on the least substituted carbon of the alkene, and then
And because no chiral carbon is made, you don't have to show that it's syn addition.
okay.
It doesn't really matter. Now this structure, you can see, actually starts to line up with this part of that final product. So this is one of the reagents to give the ether in the final product. Do you remember what is the precursor to ethers? Alcohols. Alcohols are precursors to ethers. Well, look at that. We've got an alcohol, and then we've got an ether. What do we need to react this alcohol with to make this ether? Well, obviously, I need to form a bond between that O of the alcohol and this carbon. What's the substitution of this carbon? Tertiary. So I want to have some sort of leaving group on that tertiary carbon, and tertiary carbons don't go through SN2. Tertiary carbons only go through SN1, which means I would want some sort of weak base, weak nucleophile, like an alcohol. So we actually know that this structure over here must have some other group attached that can leave, and based on the chemical that comes before it, that must be a bromine that's at that tertiary position. This does SN1. So to answer your question, yes, the product of this reaction reacts with the product of this reaction to give us this.
So it goes through that one.
It goes through that box because these two things are going to react.
I just wanted to make sure I understood that arrow.
That it is a confusing setup, and that is something that would be totally justified to like raise a question about on the exam or leave a note next to and say, here I'm assuming that this is reacting with this above. But you'll notice that that's exactly how it's done in other places where you're asked to fill in the reagent. The arrow runs through the box, fill in the reagent. And here it's the same. The arrow runs through the box, fill in the reagent. You just have to predict it based on the earlier thing. Now, the earlier thing was also blank. So how are you supposed to know the product of radical halogenation when you don't know the starting material for the radical halogenation? Well, you devised it by taking this SN1 product, this ether, and separating the alcohol from the tertiary alkyl halide. Now we can do a retrosynthesis on this alkyl halide. What compound goes through radical halogenation to give the most substituted alkyl halide? Alkanes do. And this structure is related to the carbon chain in this structure. They have the same number of carbons, and that's because they share the same alkyne precursor. So again, all of these different directions, they all feed into each other. Actually, this would be a good time for me to say this about multi-step synthesis. I give 3 tips, and I forget if I've given them to you or not. Map your carbons. This would have been useful in this problem by looking at the alcohol and how the alcohol acted as a nucleophile in this reaction down here. You'll notice I'm actually mapping more than just my carbons. I'm also mapping my oxygen and showing how it played a role in connecting the 2 structures. So mapping your carbons helps you keep track of everything and make sure you don't lose any atoms. Brainstorm. Could I do some sort of substitution reaction? Could I do some sort of addition reaction? Could I do some sort of elimination reaction? While you're brainstorming, think about the functional groups that you have. How many different ways have we seen the formation of an ether? 2. Halo ether addition. I don't see any ether, sorry, I don't see any halo group here, so I must not have done halo ether addition. And substitution, SN1 and SN2. Okay, well, I can do substitution, but I need a leaving group and I need a nucleophile. That's where your brainstorming comes in when you're doing these syntheses. What functional group do I have? What can I do with it? What functional group do I need? How can I make it? Sometimes you need to come up with more than one idea so that you can... We did talk about it because we did the multi-step synthesis and I told you those brainstormings. Okay, step number 3, work forward and backwards. It would have been impossible for me to get to this epoxide forward because I don't have any of these compounds, but I can figure it out really easily going backwards. I know how to make the epoxide. After that, I know how to make that alkene. I don't really want to take too much time just solving all of the reactions because the answer key is there and the opportunity is yours to learn. If I just put all of them, I'm the only one having a fun time if I just put them on there. Any questions that I can answer more about this? Or do you want a chance to try and solve something out on this other exam? Do you want to take 5 minutes and see what answers you can come up with? Here's what I'll do. I'll label some of these so that all you have to do is number them on your sheet and we can talk about them together. So going counterclockwise and then going clockwise. If you've got specific questions on it or on anything else, I'll walk around and answer some stuff.
On the test, I go with like some...
Nothing wrong with it.
Okay.
Absolutely.
Okay.
All you've done is shown that the sin addition was sin. It's not incorrect at all. Yeah? It's just not relevant because they aren't chiral carbons. Does that make sense? Yeah. So go for it, because if that's how it clicks in your brain, don't throw it out. Good. How are you? Nothing. Didn't say anything. No idea.
So like trying to go both directions to see if I can get.
Yeah, actually, you'll notice on this one loop of the circle is pretty much all reagents, and the other loop of the circle is pretty much all products. I do my best on the roadmaps. I forget this, but I do my best on the roadmaps to do the same number of reagents and products that you have to predict. So you always have the same number of reagents and products to fill in. Yeah, I'm sorry guys, I know it's hard to see. This takes a lot of work. Good job.
Yeah, I just do it myself, says time, and then I rate it myself. That's
Perfect.
what I did wrong.
And did you catch this?
Yeah.
It makes more sense now? Good. This one needs, do you see how there's no hydrogen here? That's why you can't have a hydrogen now. But this one needs a base. Like bromide or water should bond to that H. I would give you points because it is valid. But most of the time, have a base that comes in to deprotonate.
Like this bond going to form alkenes and then something else. Like,
Actually, much like this.
yeah.
Yeah. This is full points. Some people like to show it that way. I usually want you to think about the base.
I need the bromine minus and then this one going.
Perfect. Hi, Jenny. No, this one's not what we want. And not quite how we should write it either. If it's Na with Na, oh, okay. No, because we're not making an alkyne, we are substituting. We're not doing elimination. We're doing alkylation.
Yeah, okay, good.
You see how mapping the carbons there can be useful? No cheating. Oh, I thought he was stealing your answers.
No, it's one page. It's easy to get lost in the sauce.
Here, you're predicting an elimination reaction to make an alkyne. But we're actually adding carbons. We're not
true.
making an alkyne. That would actually just give us this.
It's a substitution reaction.
We're doing an alkylation. This one here is predicting an elimination. But we're actually not eliminating anything, we're substituting. So I want a nucleophile that can bring in those carbons and substitute a bromine. I see what you mean, because typically we take that bromine,
We did add a carbon. I didn't even.
2 carbons. So this is where mapping your carbons can be useful. All right, I know that could not have been enough time, but do you want to go through it together, or do you want more time? Raise of hands for more time? 3 or 4? Raise of hands to go through it together? Oh, 3 or 4. There was a lot of hands not raised.
Add one more to like 2 more minutes.
All right, 2 more minutes. Good. Good. Yeah, that's your answer for number 1. Perfect.
So is that for number 6 versus 2 equivalent in the NaC2H? Is that like a reactant?
Well, you don't have to guess much at what's happening, right? Because it shows you the product.
Yeah.
Yes, 2 equivalences of that, we call it sodium acetylide, gives you that next product. And this is that precursor. So do you see how one of these bromines gets substituted, and then one of these bromines gets substituted?
No.
Yeah? Now, do you recognize the reagents that react with the alkyne? How about the Diels-Alder? Can you take your Diels-Alder product and retrosynthesize it? Mm-hmm. Mm-hmm. Mm. Mm-mm. Where'd the bromines go?
It's going through oxymercuration.
Important.
Oh, sorry. Are we looking at the same one?
Yeah.
'Cause,
Where'd the bromines go?
well, I thought with the oxymercuration the bromines went away. But
They got replaced by hydrogens.
no, I'm losing my mind. It's fine.
Oxymercuration does give ketones, but it doesn't do anything with those bromines.
Keeps them on the same.
That's right.
So would it look more like this?
Perfect. Which is important for the next step, the elimination that we see next. And if you had missed that, retrosynthesizing the Diels-Alder would actually help you figure out the need for him.
It's so hard to draw.
Good and good. Yes, it is. It's weird, funky looking.
My brain breaks down. Oh, wait.
I find first and then adding this to this.
So if we wanted to add this, what's this? What's this?
I think you can read this on the top.
Oh, it has Na,
Oh, it's hard to read.
NaC.
Let me see.
Mm-hmm. Or in other words, a negatively charged carbon
Okay.
and a
plus
sodium ion.
This one, right? Plus negative.
Yep. So that's a nucleophile, and we're seeing it do substitution here. And here's a substitution where I want that same group. So this is the nucleophile I want. What you're showing, actually, yeah, what you're showing here is how to form this, and then you're reacting it with the compound we had.
Yes, to forming this.
Yeah.
Oh, okay.
So instead, we could just summarize that by, instead of reintroducing this compound that we have, let's just introduce
This
this nucleophile. Is this at work? Is that at work? Good. Good. Yeah, okay. That's a weird way to write it. I would actually just put negative charge right there.
A negative?
Yep.
First C.
Mm-hmm. And then just leave. No need for NaNH2. If you're going to say NaNH2, you should also have the H.
Even if we're forming a triple bond? We don't need,
This is actually the nucleophile you want.
for number 3?
Mm-hmm.
So would that be the same?
So you don't have to form it. You can just introduce it.
Would that be the
Oh,
same with this
okay.
one? 'Cause
So I could say
originally had
minus-
NaH2 with this.
That wouldn't be good.
Because that would remove that and then make them both negative. They wouldn't go together.
So,
Yeah. Actually,
Just
then it would
makes
promote
sense.
elimination.
so we're not
Okay,
doing
yeah.
this reaction? Because I wrote it just because I had the understanding that it was 2 steps.
Yes. So if you want it to be terminal, then make it terminal.
Uh-huh.
HCCH, and introduce.
And we
this-
need at least the NaH or the Na.
Yeah.
NH.
Or just introduce it already deprotonated. We actually we don't want to do anything to this except substitute. So I want to introduce a nucleophile. What do I want that nucleophile to look like? Draw it.
Okay.
You don't have to show how you would make that nucleophile.
So we don't need the first step of the reaction.
Nope. Kind of like here. I didn't show you how this reagent was made. Just introduced it. All right, are you ready? Okay. There's actually, this one was interesting because it's hard, right? This is a challenge. There's so much information on here that feeds into itself. So for reagent number 1, we're looking at something very similar to the reagent that goes opposite to it. I want just one equivalence of Br2. So I'm looking for Br2, one equivalence. And the way that I was hoping you would be reminded to know one equivalence is because just to the right, I indicated 2 equivalents. I don't remember, I might have taken half a point out of 2 for not putting 1 equivalence. Going to the right, 2 equivalences would actually give this intermediate followed by this product, tetrabromoethane, which is super toxic, and we have some right across the hall. Be careful with it. All right, now dibromoethylene down to dibromoethane. This is just an alkene hydrogenation. The wrong answers here are H2 with Lindlar's catalyst and H2 or NaNH3 because those are actually inert to alkenes. I need H2 with palladium. All right, now this is where I saw a lot of you getting tripped up. This is where mapping your carbons becomes really useful. Here's carbon 1 and 2, and here's carbons 1 and 2, and 3 and 4. I need to add carbons in this step. What a lot of you guys showed me was NaNH2 excess, which actually would have brought us back up to the starting material. Not good. It would have just done elimination between 1 and 2. My question is, where are carbons 3 and 4 coming from? Well, carbon 2 has a leaving group that has been substituted, SN2, by a strong nucleophile, carbon 3. Carbon 3 must have a lone pair on it. Here's carbon 3, here's carbon 4, We actually didn't look at this as much in the SN2 section. We talked about it in the alkyne section, and we called it alkylation, but it was an early example of SN2. Now that's one way that you can draw it. Another way that you can draw this reagent is like this. You can give it a counter ion. And that's exactly the reagent that we needed here. So the answer to number 3 was already given as a reagent on the other side. That was part of like the Easter egg of this problem. The answers were under your nose. Then I decided not to make this a question you had to fill in because I knew people were going to give me the wrong base. They were going to give me sodium hydroxide. And sodium hydroxide here would prefer to substitute rather than eliminate. So I gave this one. And now I have a multi-step synthesis going on. I need to do something with this to get something so that I can do a Diels-Alder product. So I'm going to go back to the other side. My tetrabromoethane is going through 2 substitutions. You'll notice that I didn't want you to predict how those substitutions were going to go. I wanted to tell you, make sure that each carbon gets substituted once. And then we've got oxymercuration. So that's an alkyne reaction. This is another place where it's really important to map your carbons. I had a lot of students in the spring that lost carbons drawing this product because transforming the alkynes into the more linear chain it gets confusing. 2 becomes a ketone, 5 becomes a ketone, and then just walking around, the thing I noticed the most, the bromines got lost. But nothing's happening to bromine in this oxidation. Nothing's happening to this bromine either. That's important because my next step is sodium amide, which is useful for doing elimination reactions, which is what you guys were suggesting back here. I've got a vicinal dihalide, 2 equivalences of sodium amide, which means I can eliminate them and form an alkyne. But maybe I'm not confident in that reaction. So I'm going to head over to the Diels-Alder product. I'm going to map my carbons, and I'm going to retrosynthesize it. Do you remember how I tell you to map your carbons on the Diels-Alder product? Yes. Good. The double bond should always be between carbons 2 and 3. There are 2 double bonds. The electron withdrawing groups should be connected to 5 and 6. What are the electron withdrawing groups? The ketones here. So these groups are the electron withdrawing groups of the dienophile. So that's carbons 5 and 6. So it's my other alkene that will make the diene, 1 through 4. And I do tell you that it's the 2 and 3 will always have the alkene, and that's usually on the left. But there are chemicals that can be a dienophile on both sides, and it can flip around, just to be fair. The electron withdrawing groups here was a great pinpoint for me breaking these back. What bonds am I going to break? As I predict the starting materials, what bonds do I break? Bromines? I don't see any bromines. 1 to 6. 4 to 5. 1 through 4 is which chemical, the diene or the dienophile? Diene. 1 through 4 is the diene. So here's my diene, carbons 1 through 4. And now I just need to take but-1-ene-3-ine and get down to buta-1,3-diene, which means I need to take an alkyne and turn it into an alkene. Because it's not trans or cis, there are two reactions that work for this. I can use H2 with Lindlar's catalyst, or I could use sodium in ammonia. Now 5 and 6, the dienophile. Sometimes the dienophile is an alkene that reacts with the diene. Sometimes the dienophile is an alkyne that reacts with the diene. Based on the information here and here, what functional group exists between 5 and 6? An alkene or an alkyne? Alkyne. Because the Diels-Alder reaction always consumes one pi bond from the dienophile. And if I have one left, I must have had two. Plus, my vicinal dihalide is the precursor to the alkyne. So 5 and 6 are connected by an alkyne. And then they've got their carbons connected to them. It's tough, but isn't it fun? You just took a 2-carbon starting material and you made a 10-carbon product with 2 alkenes and 2 ketones. Congratulations, you've mastered organic chemistry. 1.
On that bottom right one, if you put it cis or trans, would you mark down the other
The alkyne. So you're asking if you had given me this, how would I have graded it? How do you think I should grade it? Something wrong with it? It's a linear functional group. So those alkynes are linear. To be fair, no, I probably wouldn't have taken points off. That's a 2-point reagent, a 2-point product. Maybe I would have taken a 1/4 point. Probably not even a 1/2 point. I would have taken off less points for this than I would for not showing one equivalence up above. Why? Because you have the right number of carbons, you have the right number of bonds, you have the right functional groups, but you're doing the age-old issue of drawing zigzags on linear carbons, and it's something I've seen before. It's something I'll see again. No, you don't need heat here. In fact, because we're doing substitution and we want to avoid elimination, we have a strong base, strong nucleophile. We could actually say low temp. If we did do this with too much heat, we might actually do elimination. So as written or with low temp would support the substitution reaction. Does that make sense? Do you remember the reactions that we said had competition between elimination and substitution?
Yeah, so if like I was having doing one of these on the test, it's based on if it has a strong nucleophile?
Yeah. We did say that primary carbons pretty much always go through SN2, except for tert butoxide, which can go through E2 as well. Tert butoxide can eliminate. Most other things will just substitute. I guess I'm talking about realistically, if you were going in the lab, I would say avoid too much heat, because that table is idealized. It's in a perfect world. If you added heat here, I probably wouldn't take any points off because it wouldn't affect it based on what we covered in class.
In my mind, for 5, when you use Lindlar's, you get the Z conformations.
for an alkene
Right.
that has a stereoisomer.
So with Na and NH3, would it not be?
The problem is that the alkene made by a terminal alkyne cannot have stereochemistry. I already have CH, and now I'm going to make it a CH2. That alkene with a CH2 will never be cis or trans, because the definition of a stereoisomer alkene is that both carbons have two distinct groups, such that swapping any two groups on either carbon makes a unique alkene. I think what you're asking is, how do I prevent it from doing this?
Yes.
Anybody? How can you prevent this?
That's what I would think that Na and H3 would give you.
And you could easily write this and you'd get the right answer. Full points. This is S-trans conformation and S-cis conformation. All you're doing is rotating around a sigma bond, Newman projection style.
Oh, because that center bond is a sigma bond? Oh, I thought it was locked because of the... Yeah.
All you're doing is rotating around this bond. It's not a locked diene. Remember, our locked dienes are something like this.
Yeah.
Usually involve some sort of ring, and they lock because they can't rotate. So if you gave me this, full points, because it is this. Okay, now back to what I was saying before. This alkyne cannot make a stereoisomer. It cannot make a stereoalkene. There is no E or Z. What's the high and low priority on this carbon? Low is hydrogen, high is carbon. What's the high and low on this carbon? There is none. No stereoisomer. No cis or trans, so I can use either one. Good. I also tend to put reactions in the roadmap that are not used in the multiple choice questions earlier in the exam. So you're typically getting a full run for your money on the test, because these reactions are only showing up here and they're not showing up in the multi-step synthesis. You very well may see reagents or types of products in the multiple choice that are wrong answers that could help you come down and fill in the roadmap. I like to do that so you have at least Easter eggs throughout the exam to go grab information from. Because let's be honest, academia is pretty weird, and nobody, even the most tenured chemist, would do anything without their tools, right? Which is why you have a cheat sheet, so that you have a tool that you've committed to using that you can use on the exam. But at the same time, there's always other ways to find information. Oh, I don't think I can do this semester, but here's an interesting thing I've heard recently. I think it was in a high school. A teacher gave students the exam for 5 minutes before the test started, and they were able to have 5 minutes of deliberation on any of the questions, and then they had to sit down and take their test. What do you think that would do to your score on the exam? Would it stress you out more? Would it make you more confident? I mean, to be fair, you wouldn't have to talk to anybody. You could just get started, but I think the idea was that communication between classmates, communication in general, is what makes us so powerful as a society. And so by being able to communicate about the questions you're going to see, you might actually have more of an advantage on the exam. Think about it. All right, are we good on multi-step? Do we want to look more at Diels-Alder?
I think that alone helped me a lot.
Anybody else have follow-up questions on Diels-Alder? Okay. Then we've got carbocation rearrangements and pKa's. I'm going to turn this off.
Oh, actually, I guess one question, sorry.
Yeah.
If you had that confirmation on the left versus the one that we had under 5, the left would be different if your final product had different stereochemistry, right? If there was like you see what I'm saying? Like there's an up functional group and down functional group versus that one, they would both have to be down or up. Yeah. On your final product.
Oh, hang on. The final product did not have any chiral carbons.
Right, if it did.
So you're asking if we had something like this.
I just remember something with Gilzalder where like the two conformations are
That's more to do with the dienophile,
okay.
especially if it's an alkene. So let's do a problem.
Okay.
Yeah?
Well, I mean, if I'm the only one that.
I doubt you are.
I've got one brain cell if that helps. That's all that's
Oh, shoot, that's not what I wanted. It's a fun molecule, but it's not the molecule I wanted. I always think this is a good example one. How would you describe the stereochemistry of the two electron withdrawing groups? Trans. So in the dienophile, how should the two electron withdrawing groups be related to each other? Use the same word. Trans. Here, let's map our carbons. The alkene is between carbons 2 and 3. The electron withdrawing groups are connected to 5 and 6. I want to show the disconnect of 1 and 6, 4 and 5. I can already see my diene. I'm just looking for my dienophile. When we do the retrosynthesis, we put a degree of saturation, unsaturation back in. And if I want those groups to be trans in the product, they need to be trans in the starting material.
That's exactly what I meant. 'Cause
Yep.
it would be incorrect if you had a cis.
Which means if I give a multiple choice question for this, I'll always have something like this, something like this, and I'd probably even put something like this, because I'm mean sometimes. Right?
Yeah, I think for that one, because it's that middle bond isn't an alkene. It's because like for that one it matters because the middle is.
That's right.
I think that's why I was tripped up.
So Andy said the electron withdrawing groups are trans here, as opposed to being cis. How are the electron withdrawing groups related here? Trans or cis? No. Planar. They're in the same plane because they're connected to planar carbons. So if trans tetrahedral carbons are related by trans planar carbons, then planar carbons are related by linear carbons. We're just taking it back hybridization-wise, right? sp3 comes from sp2. sp2 comes from sp. This is not the right way to draw it, but an understandable way to draw it. Oh, and you know what? This actually does remind me of a topic I wanted to bring up, which is degrees of substitution of alkenes. I know we talked on Monday about degrees of substitution of carbons. So let's talk about degrees of substitutions of alkenes. My Diels-Alder product has what degree of substitution in the alkene? None, mono, di, tri, tetra, or penta? The alkene in the final product is tri-substituted. Raise your hand for no substitution, none. Raise your hand for di-substituted, or mono, let's go in order. Mono substituted, di substituted, tri substituted, tetra substituted, penta substituted. Okay. How do we decide? Number of carbons connected to the alkene carbons. Here's an alkene carbon. It's connected to 2 carbons. Here's an alkene carbon. It's connected to 2 carbons. My alkene is connected to 4 carbons, so it is tetra-substituted. Which of my options doesn't exist? Penta-substituted.
Wait, are we talking about the alkene as a whole or each individual carbon when we're saying that?
What do you think? Are we describing the alkene as a whole or each individual carbon? The alkene.
Okay, that makes more sense. I was like, wait, hold on. Where are we getting the 4?
I can see how that would be a reasonable confusion, right? In fact, I try and encourage you not to describe the substitution of individual alkene carbons, because it's challenging to decide whether we count double bonds to other carbons or not. For instance, are the individual carbons of the alkene primary, secondary, tertiary, or quaternary? Well, they're connected to 3 other carbons, but they have 4 bonds to other carbons. So they're quaternary carbons because of 4 bonds to carbons, or are they tertiary carbons because it's 3 carbons they're bonded to? I haven't found a good answer, so I generally try to discourage you from even using primary, secondary, tertiary, quaternary on those alkene carbons. Instead, describe the alkene as a whole. And if you need to, you can say 1 carbon is more substituted, 1 carbon is less substituted. What about my starting material? Each alkene of the conjugated diene. Degree of substitution? Mel, do you want to give this one a shot? What is the degree of substitution of this alkene? Perfect. Just die.
Yeah, I've heard that before.
No, not to a dick twitch. Okay, and again, penta cannot exist because
It's carbon.
yeah, we've got carbons. And since these are sp2 hybridized, the maximum group number of other groups that it can bond to is 4. So I can't have my sp2 carbons cumulative bond to 5 groups. I threw that in there to trick you. I've never written it before, but maybe I'll write it on your test. Who knows? Okay. Now we're good on Diels-Alder? Mm-hmm. Great. Let's talk about carbocation rearrangements. After I was able to grade your unit tests, I realized just how many of you really did need to have a grasp on carbocation rearrangements, especially their relationship to SN1 and E1. I mean, I did write the questions, but I re-remembered how much you needed to know it. So let's talk about, we wanted to look at the context that carbocation rearrangements, or like what will rearrange, what will not.
Yeah, I think
or we want to be able to predict the product of those.
The reason why I mostly put that one on the board is I think this is the thing that I'm still struggling the most with, like understanding when you need to do it.
Sure.
Yeah.
Let's talk about this. Let's talk about all of the reactions in which a carbocation rearrangement can occur. Do you guys think you could give me a list? I'm going to say could. What reactions give me the potential of a carbocation rearrangement? SN1 and E1. And also, to that effect, if I need a carbocation rearrangement, it must be SN1 or E1. It can't be SN2 or E2. What other reactions could a carbocation rearrangement occur in? HX, keep going. Acid catalyzed addition, or acid catalyzed hydration. Oh, that's it. There's not a lot of reactions that even create carbocations. And yet, it still happens quite a bit, huh? X2 addition, there's a halonium ring. Oxymercuration, there's a mercuronium ring. SN1 or SN2 and E2, they're concerted, so there's no carbocation intermediate. All right, so this is the only chance that it could happen. Maybe let's take an example of a carbocation rearrangement happening in each of these. Nobody put nomenclature on the board. You guys are good on nomenclature? Nice. There was nomenclature on the last unit test, right? On the multiple choice? Some alcohol nomenclature, alkyne nomenclature. Okay. Good. Who wants to name that top compound then? Hi, Ali. You were right there. Thank you. You bet. One.
1,4-methyl, 2
Mm. Oh, I like, yeah, okay. You caught on to something there. Any comments? 1,2-methyl-ene, no. 1,2-methyl, 1,4-methyl, 2-cyclohexene. What do you want to add? 1,2-dimethyl, I keep saying that. 1,4-dimethyl, cyclohex-2-ene or 2-cyclohexene. Anybody else want to add anything to that?
The locus starting on the alkene.
Got to start at the alkene. prioritize the alkene getting its lowest locant, not the total possible lowest locant set. Now we have these higher order functional groups. We have to prioritize them before anything else.
So would it be 2,5-dimethylcyclohex-1?
Not quite. Yeah, okay, so what's the issue with 2,5-dimethyl 1-cyclohexene? That numbering starts at one alkene position and then leaves the alkene. And when we start at an alkene carbon, we have to count through the alkene carbon. So we have no choice but to make one of these methyl groups position 3 and the other position 6. 3,6-dimethyl cyclohexene. We don't even have to say that the alkene is at position 1 because it's a ring and I get to start wherever I want to, and you want to start at position 1 for the alkene. Okay, good work. What is the name of the product that forms? And you will likely see a question like this on the exam where you have a reaction and you are asked the name of the product in IUPAC nomenclature. Almost. The two problems. Go ahead. Better, but still not quite, because you could have a lower locant set and say 2-chloro-1,4-dimethyl cyclohexane. But we're only going through this problem to talk about carbocation rearrangements. And you are predicting a product that does not have a carbocation rearrangement. So since we know that this is a reaction that could go through a carbocation rearrangement, we should check the carbocations that form and analyze them for the potential of rearrangement. Deal? Would it matter if my carbon went to 1 or 2, if my carbocation went to 1 or 2? They're the same substitution, so I wouldn't even be able to control where the carbocation went, and they're symmetric, so it doesn't matter where the carbocation goes. So 2 reasons why it doesn't matter. Let's put the carbocation on top. Can you describe the substitution of my carbocation? Good. Secondary carbocation, tertiary adjacent carbon, and the carbocation itself doesn't jump, does it? Because the carbocation is an empty seat. How can an empty seat jump? Someone can jump into an empty seat. What will jump? A hydrogen. Why is it the methyl group won't jump? It's a lot heavier than the hydrogen. And if the methyl group moved, then where the methyl group was goes from tertiary to secondary. There is no energetic stabilization. So now that I know my carbocation will rearrange to this tertiary position, what's the name of my product? 1-chloro-1,4-dimethyl cyclohexane. Can you give me the substitution product, my SN1 product in this next reaction? I'll actually aim for temperature control. I'll do low temperature here to make sure that we're only showing the substitution product. is this a reaction that risks a carbocation rearrangement? Tell me why, Yoon. Why? Well, why does it risk carbocation rearrangement? Because this is an SN1 reaction. I have a weak base, weak nucleophile, secondary carbon, low temperature. Those combinations are perfect for SN1. So my secondary carbocation forms, the hydride shifts, I get a tertiary carbocation. What functional group do I get in the product? An alcohol. What's the name? Two methyl, 2-butanol. Yeah? Prioritize the alcohol having its lowest Locant-set. All right, now this next one is harder. This is acid-catalyzed hydration. The carbocation that forms is secondary. This time there is regiochemistry. The carbocation will not form primary if it has the chance of forming secondary. This one is challenging because the next position over is also secondary, but it's benzylic. It's adjacent to a benzene, and that position stabilizes through resonance. So it will prefer to have a hydride shift to that benzylic position. Benzylic and allylic.
Oh, I remember allylic, but I do not remember having it right.
Yeah, when we put it on our list, stability of carbocations, we always said increasing substitution followed by allylic followed by benzylic. Benzylic is a weird position, but it's because of that extra resonance that it gets by being conjugated. So here's the product. What's the longest carbon chain that contains the primary functional group? Three. So that gets the prefix or the root prop. And the benzene here functions as a substituent. No, there's three. The benzene ring doesn't count as part of the longest carbon chain, but it does act as a substituent. So I can call this 1-phenyl, 1-propanol. All right, my last one. I've got 3-chloro, 2,2-dimethylbutane. And I'm doing this time water and heat. What type of carbocation rearrangement is expected? Hydride shift or methyl shift? Sorry, I got it in a weird spot. How did you know that so fast? Oftentimes when you see that quaternary carbon, that carbon that's bonded to 4 other carbons, and you're considering a carbocation rearrangement, it's logical to expect a methyl shift. That quaternary carbon has a lot to offer, but it's just carbon groups. So here's the carbocation that forms. Here's the hydride shift that occurs. Are we doing E1 or SN1? E1. So this is the carbocation before water adds on as a nucleophile or before water takes a hydrogen and makes an alkene? The latter. What hydrogen will water take? Yeah, there's 3 positions beta to this carbocation that could lose a hydrogen and form an alkene. 1, 2, 3. It's a tertiary carbon, so there are 3 positions I should consider. Should I take a hydrogen from here and form an alkene, or here and form an alkene, or here and form an alkene? What we're analyzing is the regiochemistry. What dead guy's name do we use to describe regiochemistry? This one is Zaitsev. So the question is, will E1 prefer Zaitsev or anti-Zaitsev? And which of these is that? That which is preferred. E1, Zaitsev or anti-Zaitsev? Zaitsev. How is Zaitsev's rule described? Most substituted alkene, most stable alkene, which would mean taking a hydrogen from the methyl groups or the tertiary carbon? Tertiary carbon. So for those of you that want to see the bump for this, as I think Aiden described it, water takes the hydrogen and the CH bond goes to form the alkene. And water takes the most substituted hydrogen in order to give us the most substituted alkene. Now, I think that's a pretty cool reaction. That's a cool molecular transformation, isn't it? And you could use spectroscopy to analyze it. Those of you that have looked at the test, you probably know that there is a page on the back that is all multiple choice questions analyzing several spectra for unknown reagents. So you get a chemical, subject it to the reactions we've been learning, analyze their spectra, and then determine what the reagent is. That's another one that I think is really cool, can feel very daunting, but I promise you the way that I write them is so that you are learning by answering the questions. You may not be able to look at those spectra and answer much, but by going through the multiple choice questions, you are being prompted to analyze the important pieces of the spectra. It does feel a little reminiscent of the PLO 4, the spectroscopy PLO that you all are able to submit still. Okay. The last thing is ranking pKa's. Now, I forget whose question this was. Was there any specific context you wanted to look at it in?
It was from the summer final. There's that question we had on there. There was like an alcohol adjacent to like a carbon that had a fluorine on it, I think, and then alcohol in the middle, and then there was
Huh.
it was basically ranked the substitute groups. Gay.
Doesn't sound familiar. Do you? Question 23. Thank you. Oh, yes, ranking. I forgot that I had ranking multiple choice on there. Okay. Oh. Amine, alcohol, alcohol, trifluoromethyl group. And we're just ranking 3 atoms. We're ranking OH, OH, and NH. I think I gave you guys this as a bonus on your midterm. What acronym is useful for ranking pKa's? One more time? Caryo, yep. Which stands for? Who's got C? Charge. More positive is what? better acid. More negative, better base. Generally, when all else is held true, because H3O plus is actually not a better acid than HSO4 minus. HSO4 minus is negatively charged. It's still a better acid than H3O plus. So this is a general rule. When all else is very similar, more positive things are more acidic. A stands for atom. And there are two components to analyzing atom. Sorry, just for clarity. No charges here. So charge does not help us with this ranking problem. How are the two ways that we should consider atoms? Good. In the same row, and atoms that are in the same family. Generally, it can be hard to tell acidity when you're going diagonally, unless you're going in that compounding direction. For instance, carbon is less acidic than nitrogen and oxygen in the same row. And fluorine is less acidic than chlorine and bromine and iodine. So carbon is also less acidic than iodine, because that is the diagonal that is combining those two effects. But the other diagonal is not as true. So it's really hard to compare the acidity in the opposite direction. So in the row and in a family, the larger the atom in the family, the more acidic. Who's more acidic, sulfur or oxygen? Sulfur is larger, more acidic. Who's more acidic, oxygen or nitrogen? Oxygen. In the same row, more electronegative is more acidic. That gives us our first ranking, correct? Nitrogen is the least acidic atom here. C is less acidic than A and B just based on the atom. What is R? Resonance. More resonance means more stable. So if the conjugate base has resonance, it's more stable. If the conjugate acid has more resonance, it's more stable. And in fact, I use that a lot in my OChem 2 classes. We look at a lot of different chemical functional groups acting as bases, and there's more than one atom that you could predict being a base. But the atom that has more resonance in the conjugate acid is more stable holding that positive charge. In order for resonance to exist, in order to have the capacity for resonance, a structure has to have what? Pi bonds. You can't have resonance without the movement of pi electrons, so you need pi bonds. Are there any pi bonds to consider here? So is there any chance that any of the conjugate bases have resonance? No. I. Induction. What's another way of thinking about or describing induction? Kind of electronegativity. Electronegativity definitely has something to do with it. Is that what you said? So actually, it doesn't have as much to do with the acidic atom itself so much as it has to do with electronegative atoms near it. So I think of induction. How do you guys use induction? Induction is a word we use. Induction cookers? Heat transfer? How about induce labor to make it happen? I'm making something happen. And what is being made to happen in this context? I like to think of as a pushing and pulling of electron density. Highly electronegative atoms pull electron density towards themselves. They induce electrons towards themselves. Less electronegative atoms induce the opposite way. They push their own electrons towards other things. So inductive effect is both a push of electrons and a pull of electrons. And we actually get this more, we get into this more in OChem 2 because we look at the acidity of alcohols. The more substituted the alcohol, the more push all of those carbon groups have on the oxygen, giving the oxygen more electronegativity, or giving the electron more electron density, making it a better base. And the less substituted the alcohol, the less the induction by the carbon groups, the less electron density the oxygen gets, the weaker it is as a base. But in OChem 1, we primarily focus on these highly electronegative atoms pulling on electron density. Meaning, if I put a negative charge on that oxygen, the nearby fluorines will help pull that negative charge away from O. Think of that negative charge as being a magnet. Oxygen as a base wants to snap on to something else, and those fluorines are weakening that magnet, making it less likely that oxygen snaps on to anything else.
Is fluorine like the only compound that's more electronegative than oxygen?
Yes, it is.
Yeah.
Fluorine is the only.
That's the only element that can even do that to oxygen.
That's true.
Yeah.
However, even having chlorines there,
Yeah, I mean, it would still have some.
there is still an inductive pull. Having bromines there, there's still an inductive pull.
I just think specifically having fluorine there is like a good indication of what you're trying to do.
So let's look at this. What if I put tert-butyl on this side? That's essentially the opposite of a CF3. That's a CH3. This is the pull of electron density. This is the push of electron density. So tert-butyl here would actually make D. Where do you think D would fall? I don't want to give it to him. I don't want to give it away.
See, does adding another oxygen impact how it affects nitrogen? That's what I'm curious about.
No, because that was all based on the atom anyways. Yeah.
Got it.
Nitrogen's pKa, amine pKa, is in the 30s. That's less acidic than the alkyne, which is why we can use amide to deprotonate the alkyne, because the conjugate amine is not as acidic. The alkyne anion is okay. Do you think that D is more acidic than A? Do you think the conjugate base of D is more stable than the conjugate base of A? The O negative on A has fluorines pulling that negative charge away, making it less likely that O minus acts as a base. That makes it a better acid when its conjugate base is less reactive. D, the conjugate base of D, has these tert-butyl groups pushing electron density up towards the O, making it a better base, more likely to use its electrons. So D actually falls here, less acidic than B, because B is at least a little bit closer to the fluorines, and B doesn't have that big, bulky pushing group. What's O? Orbital. And here we're looking for more S character. And this, I think, is confusing because SP, SP2, SP3, they all just have S. But SP3 is 1/4 S, SP2 is 1/3 S, and SP is half S, which is why the alkane is not very acidic. Alkene is also not very acidic, and the alkyne is more acidic because the alkyne is SP. But these are not in any particular order at all, which is terrible, right? It's just a good acronym. And there can be compounding impacts and there can be detrimental impacts. For instance, we know that carbon is less acidic than nitrogen based on the electronegativity of the atom. Unless the nitrogen is sp3 and the carbon is sp, in which case the orbital overwhelms the electronegativity effect. So there's no intuitive way to know how all of these work together and against each other, which is why I do my very best to give you examples that only compound in the same direction. Like this example, where you're comparing atom and induction. All right, 12 minutes. Time is yours. Number 6 on the practice final. Did someone else raise their hand too?
I had a clarifying question on the S character. So sp3 is more acidic than S in the orbital ring.
S only exists on hydrogen and helium.
So less acidic. So it goes down to S, sp, and as you add more bonds, it's more acidic.
No. Actually, the pKa of sp carbon is about 25, and the pKa of S hydrogen, which is the only molecule that has an S hybridization, because it's not a hybridization, this is actually about 44. So that idea of more S character, it actually doesn't apply to just S. It doesn't apply to hydrogen. Because we would expect then that hydrogen would be more acidic than the sp carbon. But instead, hydrogen is in the same range as the sp2 carbon. And again, the compounding effect. So an sp hybridized nitrogen, which has a positive charge, is much, much more acidic. I don't know if I could show that without a positive charge. It's much, much more acidic than an sp2 hybridized nitrogen. Yeah. So no, we can't actually take that rule of S character and apply it just to S, because that would mean just hydrogen, H2, and it doesn't apply. Mel and then Elliot. Oh, you're right. Yeah, sorry. All right. Yoon, you wanted to see this problem. Nope. Yeah, you're right. Thanks. What type of reaction is happening? X2 addition, halogenation, in the presence of an alcohol, which makes it haloether addition. You'll notice for question 6 on the practice final, the halogenation product is not listed because I didn't want everyone to lose this question. Some of the answers are substitution of the OH with bromine. We know how to do that. HBr or PBr3, not Br2. One of the answers is halohydrin addition, but there's no water present. There's no water shown. So halohydrin doesn't make any sense. The other two products are cyclic structures. Oh, and you know what? I may have had an error in this problem. No, I don't think I did. I've definitely made an error on a problem like this before, though. These are the two other options. The structure on the left, if you map your carbons, actually works out. Position 1 attacks position 2, 3, 4, 5. 1 attacks 2, 3, 4, 5. You can see the methyl groups on 3 and 4. And you can see that position 2 also has another carbon coming off of it. That's where the bromine adds. Halonium ring forms between 2 and that CH2 group, and the alcohol does an intramolecular reaction, an intramolecular haloether addition. And the alcohol attacks where? At the more substituted carbon. It attacks at the more substituted carbon of the alkene. So the intermediate bromine is here. And the alcohol attacks intramolecular. The other product is also cyclic. It's a geminal ether halo group, not a vicinal ether halo group. And the halohydrin addition, haloether addition, gives a vicinal product. How many degrees of unsaturation? The two-chicken rule is the foolproof way to find your degrees of unsaturation. I did not come up with the two-chicken rule. I stole that. But it works so good, right? 2 subtractions, 2 addition, multiply by 2, add 2, divide by 2. And it spells chicken. Remember the key element that is not a part of the two-chicken rule? Oxygen never shows up. Does not matter how many oxygens are in your molecule, it does not impact degrees of unsaturation. So you can foolproof plug in your chemical formula into there, but what were our rules for degrees of unsaturation? They come from pi bonds and rings. Because those are bonds that could have added other groups, but instead you're doubling up within the molecule. So Mel, how many pi bonds in the starting material? How many degrees of unsaturation? How many pi bonds in the product? How many degrees of unsaturation? Still a ring. 1 degree of unsaturation. I gotcha. Pi bonds and rings. If a chemical formula tells you that there are 2 degrees of unsaturation in the chemical formula, how do those degrees of unsaturation manifest? You could have a pi bond and a ring. You could have 2 pi bonds. You could have 2 rings. And those 2 pi bonds, it could be 2 separate pi bonds, or it could be, 2 separate double bonds, or it could be 1 triple bond. Exactly. Lots of combinations. Do you guys remember that day we did structural isomers? And we found that there was 2 degrees of unsaturation, so we had all these different bicyclic structures that we could do. I think we didn't draw all of them. I think we gave up after a while. Man, life was so good back then.
Did you say there were 16 or like, wait, never mind, there's 32 or something? I remember that.
I don't, it's not easy to calculate how many structural isomers are in a structural formula, a chemical formula. Octane has something like hundreds of structural isomers. Octane, 8 carbons, hundreds of structural isomers. Yoon, did we answer your question enough here? Do you feel more confident on it? Okay.
Could you go from the original structure to that one that has 6 carbons, the ring that's to the right of it?
No.
We don't know anything.
Nope.
Okay.
Because, first of all, this carbon would need to be electrophilic. It would need to accept electrons from the oxygen and also from the bromine. And then somehow there's a hydrogen that needs to get to this carbon where there wasn't before. No. Actually, Will, right after Elliot.
I was just, for your, back on the acid one,
Yeah,
are you saying A is the most acidic?
absolutely.
Okay.
I did not put my arrows, did I? C is less acidic than B is less acidic than A, and D fell less acidic than B, but still more acidic than N. C. Will?
So the 4-carbon ring with the oxygen is the major product form, just to confirm, is that what we're saying?
Yes, this one.
So, wait, what was the reaction that you said happened? Like, what was the name of the reaction?
Anybody? Halo ether.
Where in the notes did we talk about that? I'm struggling to find it. I don't know why I can't find this.
I think what you're expecting to look for is a cyclic product. We showed a lot of halo ether. It's one of the mechanisms we learned how to draw that has a separate alcohol.
I'm starting to get lost in these worksheets.
No, I know, that's the downside of the worksheets, isn't it? What could I do to improve the worksheets going forward? Number them?
I don't even think that there's necessarily
Big title? Give you guys a folder. My 5th grade teacher had to get me a planner because I was a mess.
honestly, I don't even think there's really anything wrong with the worksheets. I'm just not very organized on them. I don't have them in order.
So, Will, if you're looking for a cyclic product, you might not find it.
Yeah, no, I think I was just more confused.
What I want you to look for is vicinal halo ether. That's the product of our halo ether edition.
Yeah, I found it now. Okay, now I just couldn't remember where we first talked about this, so I was getting confused. That makes sense.
Kiara, what you got for me?
I was gonna ask, so more acidic is a lower pKa.
Correct. More acidic, lower pKa. And that comes from Gen Chem 2, right? Where pKa is negative the log of the equilibrium, the acid dissociation constant, negative the log of the Ka. So the larger the numerator, which is the concentration of product, the more positive the number, or no, greater than 1, the number is greater than 1, which means Ka is greater than 1, and negative the log of that is now negative. So sulfuric acid has a pKa negative 10. Hydronium, H3O plus, has a pKa negative 3. And acetic acid, vinegar, has a pKa around 5. More negative, more... I'm saying lower. I don't like that. More negative. More negative pKa, more acidic. More positive pKa, more basic. terrible acid.
So the ranking on the board is the acidity, right? Not the pKa.
Not pKa. What did the question ask for?
The question is asking for pKa, so you have to flip it, that's fine.
Exactly.
Oh, that's terrible. It didn't list them as A, B, and C either, right? It listed them as I, and I. So I plead the fifth. Thanks for pointing that out. Yeah, I should have looked more closely at that.
It still made sense.
Congratulations, guys. You have made it to the end of OCHEM 1. Monday night, 5:50 in this room. Bring with you a cheat sheet, 2 sides, or two sheets, one-sided, or the equivalent of that surface area in note cards. Whatever you like to do. I had a student that asked to do note cards, and why would I stop him? Did it by units or something. I think I plan on starting right at 5:50. So I'll be here around 5:40, maybe 5:30, just to get set up and be ready. So if you have last-minute questions you want to ask, come early. But otherwise, we'll get started right at 5:50. Okay? Have a good weekend. Happy studying. I'll see you on Monday.